In lesson 2.3, we are going to introduce two really important concepts. First, we're going to look at something called a factorial. Then we're going to look at permutations. And again, they're both things that are going to help us count up what we're looking for. So let's start with factorial. Factorial is a product of sequential natural numbers of the form and shown below. So that's just before I get to the little formula, there's some important words here. So natural numbers are the numbers 1, 2, 3, 4, 5. It's like no decimals, no fractions, doesn't include the number 0. It's just if we were counting things. You know, 1 banana, 2 bananas, 3 bananas, we'd use natural numbers. Sequential means that we're going to do it in order. And so, a factorial looks like this. It's got a number, n, with an exclamation point beside it. That exclamation point is a math symbol, or at least we're using it as a math symbol, and it just means factorial. And so it means take this number n, whatever it is, and then multiply it times 1 less, and then 1 less again, and keep going until you get down to 1. So that'll be clearest if I just do an example. So 4 factorial, using this formula up above, means start at 4, then multiply it by 4 minus 1, and then multiply it by 4 minus 2, and then multiply it by 4 minus 3, which is the same as 4 times 3 times 2 times 1. And that's why I stopped at 4 minus 3, because I knew that I had to stop when I got to 1. So it's just taking the number, whatever that number n is, and multiplying it by 1 less until you get down to 1. So 4 times 3 is 12, times 2 is 24, times 1 is still 24. So 4 factorial is equal to 24. Now, most calculators have a factorial button somewhere on them. Let's see if my iPad one does. It does. If you look over on the left-hand side, you'll see an X factorial in the very left-hand column, 2 rows down, or 3 rows down, I guess. So if I do 4 factorial, I do 4, hit the factorial button, and you can see in the top right, it tells me that 4 factorial is indeed equal to 24. So 6 factorial would be the same as 6 times 5 times 4 times 3 times 2 times 1. Whoops, forgot my brackets. 2, 1. All right, which I can expand out, but I could even think of it, since I know that 4 times 3 times 2 times 1 is just 4 factorial, it's just the same as 6 times 5 times 4 factorial. And I don't need to write it like this, but I'm just pointing out that it's the same thing, because I already know that 4 factorial is equal to 24. And, you know, just mentally I could go, okay, 5 times 24 is 120, times 6 is 720. You know, that's not the only way to do it, of course. It's not even a logical way to think about it under normal circumstances, but I'm trying to point out, you know, that they're equal. So if I go 6 factorial, yep, that's equal to 720. 10 factorial, well, now the numbers are getting a bit bigger, so let's just use the calculator button, right? I mean, that's what it was invented for. 10 factorial, 3,628,800, if I remember correctly. So calculator is definitely handy, especially since, as we can see, factorials tend to grow very quickly. 4 factorial was 24, 6 factorial was 720, 10 factorial was over 3 million. Now, we could just type this into our calculator, and let's do it, but I'm going to show you, after we do it, I'm going to show you another way to think about it as well. Actually, I'm rethinking that. Let's do it the other way first and then confirm it on the calculator. We know that 11 factorial is equal to 11 times 10, well, let's use brackets since that's what I've already been using, times 10, times 9, etc., down to times 2 times 1. We know that Well, actually, let's go a little farther. Sorry, I just keep rethinking things as I go along. Let's go down to 8, 7, and then go dot, 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 down to 2 times 1. We know that 7 factorial is just 7 times 6 times 5, etc., down to times 2 times 1. Since this is all multiplication, I can cancel things out. Like the 1 cancels the 1, the 2 cancels the 2. You know, the 5 and 6 would cancel with numbers I didn't write, but they were in there. 7 cancels the 7. Really, all we're left with is these 4 numbers that didn't cancel each other out, the 4 biggest numbers in the numerator. So that's 11 times 10 times 9 times 8. 11 times 10 times 9 times 8. 7,920. So it's good to understand that that's how it works. Of course, I could just do it in my calculator. I could go 11 factorial divided by 7 factorial. And I get the same answer, but where's the fun in letting the calculator do all the work for me? So that's factorials, and we're going to use that to help us understand permutations. So before I talk about a permutation, I want to talk about what an arrangement is. Put a nice little box around that. Beautiful. So an arrangement is an ordered list of items. Okay. How does that come into terms or into play with permutations? When an arrangement of items needs to appear in order, so an arrangement already is implying order, then it's called a permutation. Okay? All right, great. Permutation. There are n ways of selecting the first item, n minus ways of selecting the second item, n minus 2 ways of selecting the third item, and so on, until there's only one way of selecting the remaining item. Using the fundamental counting principle, multiply these numbers together, you get n times n minus 1 times n minus 2, etc., which you may recall is just n factorial. So the number of permutations of n items is npn equals n factorial. So this is an important formula which I'll need to explain to you, and I certainly will, although not quite yet. I'm going to just go through a little example and then talk about that formula. So how many 3-letter words, and by the words is in quotations because it doesn't have to be real words. In other words, how many ways can we arrange the letters A, B, C? Well, in the last lesson, we saw that one way that we can think about things is we can draw out the number of spots. So there's 3 letters, and we can think about how many ways we can fill each of these spots. So for this first spot here, I haven't used any letters yet. It's like drawing them out of a bag or something like that. I've got 3 choices, right? So I've got 3 options to put in this first spot. Let's say I picked A for my first spot. Well, then I've got B and C left. I've got 2 choices left for my second spot. Or if I pick B for my first spot, then I've got A and C left, but I still got 2 choices. Or C, if that goes in the first spot, still got A and B left. I've got 2 choices even still. No matter what letter I pick for the first spot, there's 2 left over to put into the second spot. And after I've chosen the first and the second spot, there's only 1 letter left, and it has to go into the third spot. So using the fundamental counting principle, we can see that there's 6 ways to fill that first spot, or to fill those 3 spots, and so we can make 6 words, again in quotations, out of that. But as you can see, 3 times 2 times 1 is nothing more than 3 factorial. And again, 3 factorial is just 3 times 2 times 1, so of course that does equal 6. So let's tie that back to the formula. I said I'd come back to it. So npn equals n factorial. So here's what the different letters stand for. The first little n there, this one, is the number of items that we have to choose from. And the second, no, that's, yeah, let's say that. So the second n is the number of items chosen. Because they're not always the same. I might have 1,000,000 items to choose from, but I only want to choose 3. Or to take smaller numbers, maybe I have 7 items to choose from, but I still only want 3, for example. So that first n and that second n are not the exact same thing. Although, as I say that, I realize they are the exact same thing in this case. Later on, we're going to see another version of this, this NPR one, and they are going to be different. In this case, because we're using n for each, it does mean that we're actually choosing all of them. So if I have 3 items and I want to choose all 3 of them, then yes, they will be the same. P actually just stands for permutation, just for the word permutation. So if I've got 3 items to choose from, 3 letters, A, B, C, I got 3 to choose from, and I want to do all 3 of them, then that's going to be equal to n factorial, which is 3 factorial, which is what we've already got, which is equal 6. However, and I don't think this is on my iPad calculator, most calculators should have permutation options on them. My calculator doesn't. So I'm going to have to just switch to my real calculator and show you. So let's see. Turn on my camera. And here's my actual calculator. And if you notice down there above the number 3, you'll see it says NPR. So here's how I type it in. I type in, if I want to do 3p3, I'd hit 3. Then I'd go second function. Then I'd hit the 3 again because it happens that NPR is just above the 3. So I'm hitting this button again just to get the NPR. So you can see that P came up on my screen. And I'm going to hit 3 one more time so that it says 3p3, which is what we saw. That equals 6. So 6 factorial. What if I had 4 things to rearrange? We already saw that 4 factorial is equal to 24, so does 4p4 equal 24? Yes, it does. We already saw that 10 factorial was 3 million and something. Let's do 10p10. In fact, we got the same thing again. So this p, NPR, really does give us use factorials to work things out. All right, so that's equivalent. That's how that works. Now that was arranging all the items, but we don't have to arrange all the items, as I've already said. That thing I've written in baby blue where it says number of items chosen can in fact be any number less than n. It's possible to choose, let's say I've got 26 letters in the alphabet and I want to randomly arrange as many 3-letter words as I can, well then n would be 26, but r would still only be 3 in this case. So permutations of r items out of n items would be, we still start out with n as our first factorial number, which is going to be then multiplied by n minus 1 down to n minus 2, but we don't go all the way down to 1 this time, right? We don't go times 2, times 1. That's not here. We stop before that, so that's a no-no. I'm going to get rid of that. We stop at n minus r plus 1, which is just really the equivalent of the kind of thing I was doing up here. N factorial, take away, 11 factorial divided by 7 factorial, I took away from 7 down to 1. That's really what's happening. I'm taking away all the extras. I just want to take 3, or the number that I want. Let's say not 3. I was thinking of a particular example. but I want to take a certain number of them, and it's the highest value of them. So again, we've got n, which is our number of items to choose from, but in this case we've got r, which is the number of items that actually are chosen, which can be any number less or equal to n, and of course p equals permutations. So let's see how we can actually use that. There's 12 different swim team members. There are 12 different swim team members to compete in 4 lanes in a pool. How many arrangements are possible? Solve using each method. Sure, so we got 12 members of the swim team. That's the number that we can choose from. There's 4 lanes in a pool, and generally they only let one person in a lane at a time. Things get too crowded otherwise. So we got 4, we can fill 4 places. So fundamental counting principle, we got these 4 places. So I pick one of the 12 to go into the lane number 1, let's say, and then another one to go into lane number 2. So I guess, let me backtrack for a second. The reason why I wrote a 12 in that first number is I've got 12 choices, right? There's 12 members of the team. I could pick any one of those 12 to go in the first lane. But once I put a person in the lane, let's call her Sally. Once Sally's in that first lane, then I can't choose her for the next lane. So now I've only got 11 choices. And then once there's 2 people chosen, now I've got 10. And then I've got 9. So using the fundamental counting principle, I've got 12 times 11 times 10 times 9 different ways of arranging them. And order does matter, by the way. So I said Sally's in lane number 1 maybe, but Sally could also be in lane number 2 or lane number 3 or lane number 4. They could be the exact same 4 people I choose, but in a different lanes, and that would be a different arrangement. Anyway, let's go to the calculator. 12 times 11 times 10 times 9, 11,880. So that's using the fundamental counting principle. Using permutations, there's n members to choose from, so n equals 12. There's 4 lanes. I can only fill up those 4 lanes, so r equals 4. So I would do 12 choose 4. Sorry, not choose. I gotta be very careful. Choose means something else. I gotta do 12p4, which I know is going to be 12 factorial over, using this formula, n minus r factorial. Minus 4 factorial. I just don't have the formula on the screen, so I'd like to show it to you again. Let me zoom in here. Remember, the formula was NPR equals n factorial over n minus r factorial. So that's the same as 12 factorial over 8 factorial, which we know means that the 8 factorial, each of the numbers in 8 factorial is going to cancel out with the 8, 7, 6, whatever down to 1 in the numerator, leaving only 12, 11, 10, 9, like we got for the fundamental counting principle. So I could do that on my calculator like this. 12 factorial divided by 8 factorial. And as you see, I get the same answer of 11,880. But again, I've got a calculator that can do 12p4, so why would I not use that? I'm just grabbing the calculator here. 12p4 equals 11,880. So we get it that way as well. You own 8 books in a series. How many arrangements of books all in a row are possible if there's no restrictions? So in part A, n equals 8, and we're arranging all of them, so we just want npn, which is 8p8, which is the same as 8 factorial 40,320. So that's a lot of arrangements. The first 3 books of the series must be together in order at the beginning. So we got a restriction here. And each one of these things I'm highlighting in a different color has a bearing on it. So let's imagine, again, let's think about it. It's always helpful to draw a diagram if things start to get a bit complicated. So there's my 8 spots. And I've got the first 3 books have to be together in order at the beginning. So if I'm straight from the left, that means that book number 1 of the series must be in spot number 1. So there's only one way I can do that. And book number 2 of the series must be in spot 2. Of course, there's still only one way I can put book 2 in spot 2. Same with book 3 must be in spot 3. So those 3 are locked in. There's only one way to do it. But the other 5 can be arranged any way I want. So there's 5 choices for the next spot. But then once I picked 1, there's only 4 more left. So there's 4 choices. Then I pick 1 and there's 3 left. Pick 1 and there's 2 left. And then the last book has to go in the final spot. So we can use the fundamental counting principle again to help us see that really this just boils down to 5 factorial, because those 1s at the beginning don't matter. They're going to, 1 times something doesn't change it. And I know I don't even need the calculator because I remember from earlier that 4 factorial is 24. So 5 factorial would be 5 times 24, which is 120. The first 3 books in this series are to be together. Okay, we've already seen that. In any order. Now that's a little different. And in any position. That's also different. All right. Can't really draw this one out quite as definitively as I can in the previous example, but I can still draw a diagram to help me think it through. So let's pretend, for example, or for helping us, for instance, that those first 3 books are still at the beginning. I know that they can be in any position, so I could have the 3 books in these, they could be in that position, or they could be in this position, or they could be in this position, or they could be in this position. I might as well go through them all at this point. Or they could be in this position. How many times different circles did I just draw? If you go back and count them to yourself, you'll see I had 1, 2, 3. That's getting messy, isn't it? 4, 5, 6 different ways I could circle 3 of them together. So there's six ways that I could deal with in any position. So I'm keeping 3 of them together, but in any position, that gives me a number 6 to keep track of. Let's pretend, though, that they're at the first 3. They're in position 1. So this is our group of 3, because I have to draw them somewhere, so I'll just pretend it's here. Within that group of 3, they can be in any order. So I still got, it doesn't have to be book 1 in the first spot. It could be any one of the 3 in the first spot. But as soon as I pick one, now there's only 2 left. And then there's that last book which has to go beside it. So that first 3 books of the series do have to be in this order like this. And then, and we know that 3 times 2 times 1 equals 6. So maybe let's write this 6 up here. And then what's left? We still have those 5 other books left. So we got 5 choices for that next spot. And then I use it up and I got 4 left. And I pick one and I've got 3 left. And I pick one, I've got 2 left, and so on. So that's 5 factorial, which we already saw was 120. So we've got the 6 books of the first 3 times the 120 books of the other 5. But remember, they could be in any position. I should have done that in a different color. I'm going to change it now. Let's make it green. But then I can have them in any position, so that gives me 6 more options. So 6 times 120 times 6 is going to equal 6 times 120 times 6 equals 4,320. So things can get tricky when we're counting stuff, when they start putting conditions, and that's where really understanding how the permutations work, how factorials work, and drawing a sketch like this to think things through logically is definitely going to be very helpful to you. So take a look at the homework questions and see what you can do with them. Good luck.